This video will focus around the concept of KW, both what the concept is as well as how to solve problems about it. So far we learned in acids and bases kind of what an acid and what a base is. Acids essentially, by definition, regardless of whether you use Arrhenius or Bronsted-Lowry, is that they have H plus to donate. And then bases, either for Arrhenius, they have OH, or for Bronsted-Lowry, bases can take on the hydrogen. Either way, there's kind of like this OH piece. So H should be acid in your brain and OH should be base in your brain. Now something that's super cool slash super crazy about water is that water is kind of our universal solvent. It can kind of dissociate or ionize most salts. But it turns out water is so polar, water actually ionizes itself. So as water is moving around and bumping into itself, some of the H2O is splitting up into like an H plus and an OH minus ion. And as it does that, okay, that's what we call self-ionization. So that process can either be represented like on the screen where two waters hit, one H is transferred over to one water, thus making a water OH minus without the H and H3O plus with the H. Okay, or you can just think of it as one water that breaks apart into H plus and OH minus. Okay. When it does this, what I would always say is that this H plus or the H3O plus, depending on how you write the equation, that's essentially your acid part. So acids always have hydrogen to donate or essentially are creating hydrogen in solution. And then this OH minus is basically your base part because bases are always creating OH minus. Okay, language-wise, H3O plus is called the hydronium ion. Okay, so we have the hydronium ion is the H3O plus, and then the H plus is just called the hydrogen ion. And then OH minus we already know is called hydroxide. So we have lots of H's here, hydronium, hydrogen ion, and hydroxide, but all of those have to do with acids and bases. Now, while water is self-ionizing and making H plus and OH minus, essentially for every H plus it makes, it's also making an OH minus, which means you have equal concentrations of acid and base within water. Now, something I always thought was really crazy is that while acids and bases are so important and we think of the pH scale and you guys are, know some about that, the amount of molecules that actually self-ionize in water is very, 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 very tiny. Okay, so imagine you had a whole liter of water, and a liter is maybe weird for you to think about, but it's about a quart. Okay, or you can think of a liter, bottle of pop. In a liter, you have about 55 moles of water, and in that 55 moles, only 1 times 10 to the negative 7 of those moles are actually ionizing. Right, of the 55, 1 times 10 to the negative 7. It's so tiny, right? But because H and OH affect the chemistry that can happen in the water, any amount of H or OH is really, 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 really important. So what's weird about acids and bases is it's usually a really small amount of H and OH that can affect a whole system. And because we live in this aqueous environment where like our body's aqueous and the wildlife is aqueous and most of the food we eat is aqueous, this H-OH balance is really important. Okay, so in neutral water where I have the same amount of H and same amount of OH, that means I'll have that 10 to the negative 7 of H and 10 to the negative 7 of OH. So if that's how many waters are dissociating, that's how much H and OH I'll make, moles in 1 liter. Okay, so in a neutral solution, H and OH are equal, and they'll be in a neutral solution, they'll have a concentration of 1 times 10 to the negative 7, always, moles per liter. Right, so if you have more liters, you have more moles, but the ratio is always 1 times 10 to the negative 7. Maybe that negative 7 starts to ring a bell because potentially the pH of water is 7. So this is an equilibrium reaction, just like we've seen. So you can create an equilibrium expression for it. Okay, so H and OH are dependent on each other, right? As one goes up, one has to go down in order to keep that relationship balanced. Because in neutral, both of them are 1 times 10 to the negative 7, we could write an equilibrium expression for this, right? So we don't have water as part of it because water is a liquid, but these ions are both aqueous, which means my K expression will equal the concentration of whatever the H plus is times the concentration of whatever the OH minus is. Now, if I had done the other equation like I have on the last slide, this equation instead could sub in H3O plus, and those would be the same. Okay? So this is our equilibrium expression for water, always. And unlike in our equilibrium last time, where K was always like really random, this K is actually named Kw, which is the constant for water, and that K is always going to have a value of 1.0 times 10 to the negative 14. So sometimes you're doing problems and you'll be like, I don't have enough information. But you do, because K is a constant and the number is always 1 times 10 to the negative 14. So when it comes to thinking about this in relation to equilibrium, here's what you get. If I have pure water and I add acid to it, what's going to happen with acids is acids will always dissociate to increase H, right? Increase H. And if H ends up increasing, because K is a constant, OH will have to go down because this is a constant. Okay, so essentially in acidic solutions, I will always have more H, which means I'll always have less OH. Okay, so acidic or acid means H plus is greater than OH minus. These will shift, right? Equilibrium shift. If instead I have a base always increases the concentration of OH, either by donating it or reducing the H's. So if I take H's out because I'm a hydrogen acceptor, I'll make more OH because of this equilibrium. So in a basic environment, I always have more OH and less H plus. So a base means more OH. Again, that 10 to the negative 7 is right in the middle. That's where you have water. So you can kind of figure out whether you're an acid or a base solely based on the ion amounts. So let's look at some math in relation to this. The first question is, what is the concentration of OH if I know the concentration of HCl? So HCl is an acid, right? That concentration of HCl, as HCl dissociates, it's going to give me my concentration of my H plus or my H3O plus. So hydrogen ion and hydronium ion, again, the same thing. Now, I'll solve this for you guys in a second, but the question is this solution acidic or basic? Please, please, please go with common sense. I have a solution of HCl. HCl is an acid. Ergo, this is an acidic solution. I cannot have acid added to water and make a basic solution. That is crazy. Okay? Now, the other way you can tell is you can see the concentration of HCl is 10 to the negative 5. Negative 5 is greater than negative 7, meaning I'll have more H and less OH. So again, negative 7 is in the middle. So if that concentration of HCl had been 10 to the negative 10, for example, then it would have to be a basic solution because 10 to the negative 10 is smaller than negative 7. So in order to solve these, we would just plug in what we know and rearrange. So Kw is 1 times 10 to the negative 14. I'm giving you the concentration of acid, which means that's this part. And then what I don't know is the concentration of OH. So that's the part that I'll solve for. Okay? So essentially, Kw divided by the acid will give you the base. And Kw divided by the base will give you the acid. So either way. Make sure when you put this in your calculator, you do put this thing into a parenthesis. Otherwise, it will give you the wrong exponent. Okay? So you have a max for these problems. If you get anything greater than 10 to the negative 14, you probably mathed wrong because that's what our pH scale is based on. So for this first one then, if I rearrange that and solve, what I got from my calculator is 3.23 times 10 to the negative 10, and that's a concentration, so that's molarity. So that's my concentration of OH minus. You can see it's less than negative 7, and that's why it's an acid, because OH is less than negative 7. Now the next one looks identical. I'm asking for concentration of H plus when I give you concentration of the base. Again, the question is this an acid or a base? Well, it's a base. I put base in, so that's how it's a base. End of sentence. To answer this, I'll divide it over. Again, when I do that in my calculator, I got 1.45 times 10 to the negative 11. That's a concentration, so that's big M. So those are your examples of KW problems. Have a nice night. So for this first one then, if I rearrange that and solve, what I got for my calculator is 3.23 times 10 to the negative 10, and that's a concentration, so that's molarity. So that's my concentration of OH minus. You can see it's less than -7, and that's why it's an acid, because OH is less than -7. Now the next one looks identical. I'm asking for concentration of H plus when I give you concentration of the base. Again, the question is this an acid or a base? Well, it's a base. I put base in, so that's how it's a base. End of sentence. To answer this, I'll divide it over. Again, when I do that in my calculator, I got 1.45 times 10 to the negative 11. That's a concentration, so that's big M. So those are your examples of KW problems. Have a nice night.